In this discussion video, we will do a sketching example. All right, so this is problem number 3 from worksheet 11, and it says to graph f of x equals x squared minus 3x all over x squared minus 9, and to clearly indicate any asymptotes, holes, local extrema, and inflection points on your graph. So to be able to do that, particularly the local extrema, the inflection points, we're going to need our first derivative, we're going to need our second derivative. Okay, so there's going to be a lot of steps to this, and I want to first give you 15 minutes to try this problem. Okay, so because there are a lot of steps to it. So 4, 3, 2, 1, pause it for 15 minutes to try this question. Alrighty, so hopefully you did that. Hopefully you tried it for about 15 minutes. Let's talk about it together. So I want to follow our steps from class in terms of how I'm going to organize my work in these curve sketching problems. And step A, remember, was to state the domain of our function. So for the domain, I got to think about the restrictions on the inputs. So what are all the things that x is not allowed to be? What are the restrictions? And with this fractional function, the only restriction is that the denominator should not be equal to 0. And because of that, if I think about what would make this what would make that denominator be 0, the only things that would work are x is 3 or negative 3. So we just need x to not be those values. So our domain is all reals except for those numbers. All reals except plus or minus 3. All right, so we are ready for step B, which is to get the intercepts. So to get the intercepts, so remember our function, our original function, was f of x equals x squared minus 3x over x squared minus 9. And all right, so for the intercepts, let's start with the y-intercept. And for the y-intercept, I set the x coordinate equal to 0. And if I were to plug that into here, it turns out that the y value is 0. I'm skipping showing that work because I want to, in general, I'm going to go quickly through the arithmetic because I want to spend more time talking about the key concepts. All right, so what about the x-intercept? This one's a little bit more involved, so I'll work it out. I'm going to set the y value equal to 0. So I'll get 0 equals x squared minus 3x over the x squared minus 9. And I can multiply both sides by the denominator. And on the left, I'll get 0. On the right, I'll just get x squared minus 3x. And now I could factor to get 0 equals x times x minus 3. So we get x equals 0 and x equals 3. But I have to be careful. If I have an equation that I'm solving that has variables in the denominator, I got to check for extraneous solutions because maybe these answers would have made my denominator 0. And it turns out that 3 does make this denominator 0. So 3 is extraneous. This is one of the situations where I got to check for extraneous solutions. So we only get x is 0. So the x-intercept, remember, to find the x-intercept, I set the y value equal to 0. That we knew already. And now we know that the only one is where x is 0. So my x-intercept is also just 0, 0 here. Okay, we are on to step C, which is symmetry. Is our function going to be even or odd or neither? Okay, so the way we test this is I plug in negative x for my x into my function and see what that becomes. So that'll give me negative x being squared minus 3 times negative x over negative x being squared and then minus 9. And if I simplify this on the numerator, we get x squared plus 3x. On the denominator, we get x squared minus 9. Okay, and I got to think about, is that the same? Is that the same as f of x, my original function? Well, no, one of the signs is off. So this is not equal to the original function. Is it equal to the negative of f of x? No, that wouldn't be right either. So it's not equal to that, which means this function is neither even nor odd. Okay, so it doesn't have either of those two types of symmetries. All right, so we are on to step D, which is now to find asymptotes and holes. So asymptotes and holes. So hopefully some of these steps, or maybe even many of these steps, you got to during that 15-minute pause period. Okay, so if you notice me going kind of quickly through this, it's in part because I know that you already tried a little bit and made some progress, hopefully. Okay, and a lot of what I'm talking about now is some of that arithmetic, and I'm going to go more quickly through that arithmetic. Okay, so for asymptotes and holes, remember our function was this. It's helpful to factor that when getting the asymptotes and holes. So the numerator will factor as x times x minus 3, and the denominator factors as x minus 3 times x plus 3. Okay, and with this, the x minus 3's cancel, and I just get x over x plus 3. But when I cancel away something like that on the denominator, domain restriction, I got to make sure I include that. So this is true as long as x is not equal to 3. Because in my original function, I can't plug 3 into it, because it makes the denominator 0. That would make the whole thing undefined. So even when I simplify it, I still don't want to be able to plug in that. I can't change the domain when I simplify a function. All right, so for my vertical asymptotes, remember, these come from the factors on the denominator that did not cancel away completely, and that's the x plus 3. What makes that equal 0 is x equals negative 3. That's the equation of my vertical asymptote. We get holes from any factor on the denominator that did cancel away, like the x minus 3. So what makes that 0 is x equals 3. Okay, and to find the y-coordinate, we're going to plug this into the simplified form. So the y value will be 3 over 3 plus 3, which becomes 1/2. So in general, to get the y-coordinate of a hole, we need to use the simplified form. And we mentioned this in lecture as well. In lecture, I explained it in a little bit more detail as to why that is. Okay. Another quick thing that I might notice is if I were to plug in x equals 3 into the original, it's going to be undefined because the bottom is 0. All right. So, okay, I got vertical asymptotes, I got holes. I need horizontal ones. So for those, I have to take the limit as x goes to infinity and as x goes to negative infinity. So if I do the limit as x goes to infinity of x squared minus 3x over those x squared minus 9, I'm going to use my shortcut where I just keep the highest power terms. So this will be equal to the limit as x goes to infinity of, just keep the x squared on top and just the x squared on bottom, because those are the biggest power terms. And these cancel perfectly and just give me 1. Similarly, if we were to take the limit as x goes to negative infinity of this function, it would also be equal to 1. Whoops. Also be equal to 1. So my horizontal asymptote is going to be y equals 1. Okay. All right, so we are on to the next step. All right, and now we would need to find where is this thing increasing and decreasing, and where are the local extrema, local mins and local maxes. Increasing, decreasing, and local extrema. So for this, I'm going to use my original function. Remember our function, and I'm going to have to take its derivative. It's going to be helpful if I use the simplified form. It's just easier to take the derivative of the simplified form. So my function was x over x plus 3. At least that was the case with the domain restriction, that x is not allowed to be equal to 3. Okay, so if I do the derivative of this, I'm going to skip some steps, and I'll just tell you what the derivative is. It ends up being 3 over x plus 3 squared. And once I have the derivative, I got to think about, and I don't want to forget the domain restriction, still have that, if x is not equal to 3. So when is this derivative 0? Well, it never equals 0. Because for it to equal 0, the numerator would have to be 0. But the numerator is 3. That's never going to be 0. And I got to figure out when is this undefined. So it's going to be undefined when the bottom is 0, which happens when x is negative 3. Okay. And this is where I have to remember my domain restriction. Because x being 3 was not even in the domain, my function, my derivative is technically also undefined when x is 3. That's not in the domain. Not in the domain. That is a place where my derivative is going to be undefined. Okay, so I go to make my number line now. And I have to put -3 on it as well as 3. All right, and I'm going to keep track of the factors of my derivative. So the 3 and the x plus 3 squared. And from there I can form my derivative and keep track of the original function. Okay, so I'll separate out rows. And I'll separate out columns. So for 3, that's clearly positive. For x plus 3 squared, because that even power, that's never going to be negative. Okay, so I can put positive signs there as well. So my derivative, when I divide two positives, is always going to be positive. And when my derivative is positive, the original function is going up. It is increasing. Here as well, increasing. And here as well, it is increasing. So writing that down, my function is increasing on -∞ to -3 union, -3 to 3 union, 3 to infinity. I can't combine these even though these are consecutive intervals because my original function is not continuous at -3 or at +3. Okay, and from my number line, I can see that this is definitely never decreasing. So never decreasing. And there are going to be no local extrema. No local extrema here. For me to have a local extrema, my function would have needed to change from increasing to decreasing at one of these, and then that value where it changed would have needed to be a place where my function was continuous. So not only did my function never change, it just stayed increasing the whole way, but at these two sort of transition points or cut points, these were not even places where my original function was continuous. So in other words, these numbers weren't even places, they weren't even critical numbers of my original function. We'll see this graphically later because -3 and +3 are going to be vertical asymptotes on this graph. So they definitely can't be places where I have a local max or a local min. All right, so we are on, this is step F. We are now ready for concavity. And so plus inflection points. Okay, so for this, we'll need the second derivative. I'll just put a dot, 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 because I'm going to skip some work. Turns out the second derivative is equal to -6 over x plus 3 cubed. So even though I'm writing the dot, dot, dot here in the discussion video, if this was a homework problem, I would want you to show that work of computing this second derivative and showing those steps. Okay, so I still have my domain restriction that x is not allowed to be equal to 3. So this second derivative also never equals 0 because I would need the numerator to be 0, but the numerator is 6. It's not 0. Okay, and this is going to be undefined when the bottom is 0, which happens when x is -3. It's also undefined at this domain restriction. I have this domain restriction that x is not allowed to be 3. Okay, so it's undefined when x is -3 or when x is 3. This is not in the domain also. Not in the domain. So I can't forget that. All right, let's go to our number line. So I'm going to put -3 and +3 on the number line. And then for my factors, I'll write the -6 x plus 3 cubed. We'll do the second derivative and the original function. We'll separate out some rows and then columns. I'm going to do this number line really quickly. I'm going to skip the justification because we did something really similar with increasing, decreasing. I'm going to trust that you can check this. So -6, that's negative the whole way. And with the next row, I'll get negative and then positive, positive. So when I put it together, this is positive. That's negative, that's negative. And when the second derivative is positive, my original is concave up. And when it's negative, the second derivative is negative, the original is concave down. Concave down. All right, so our function is concave up on -∞ to -3, and it's concave down. It's concave down on -3 to 3, union 3 to infinity. I can't combine those because my function is not continuous at 3. So even though they're doing the same thing in these consecutive intervals, I can't combine it because my function is not continuous at 3. Okay, what about for inflection points? Well, inflection points are places where my function changes concavity and my function is continuous. So even though the concavity changes at -3 from up to down, our original function f is not continuous. It was not continuous at x equals -3. In fact, -3 was not even in the domain of the original function. If I plugged it in, it made my denominator 0. So as a result, this is concave up, this is where it's concave down, but there are going to be no inflection points. So with that done, we are now ready for step G, the final step, which is to graph this thing. So we start the graph out by making a combined sign chart of the first and second derivative. So I put a tick mark at any number I had a tick mark on in either the second derivative graph, which was -3 and +3, or in the first derivative sign chart, which was still -3 and +3, if I think back to when I did that. All right, and then I'll make a row for my derivative, my second derivative, and what that tells me about the shape of the original function f. Let's separate out some rows and some columns. So the second derivative, I can see its signs here. It's going to be positive and then negative and negative. And the original function, the first derivative was positive, positive, positive. All right, so if I look at this middle column, let's start with that. First derivative is positive, which means the function is increasing. Second derivative is negative, which means it's going to be concave down. So increasing concave down looks like this. So similarly, this is going to be increasing concave down, and the first column is going to be increasing concave up. That's going to be this shape. All right, we are now ready to start to put this all together. So we are graphing y equals x squared minus 3x over x squared minus 9. That was our original function. Remember, we had simplified it to x over x plus 3. Can't forget the domain restriction, that x is not allowed to be equal to 3. Okay, now let's draw some axes. X-axis, y-axis, and put some tick marks. So I'll go 1, 2, 3, 4, 5. -1, 2, 3, 4, 5. So that's 5. And then y direction, let's just go 1, 2, 3, 4. And then -1, 2, 3, 4. Okay, I'm going to draw the points that I know are on the graph for sure. So remember the intercepts we got, there was just one, and it was at 0, 0. All right, so there's an intercept at 0, 0. All right, and then I want to draw in asymptotes. So there was a vertical asymptote. So there was a vertical asymptote at x equals -3, and a horizontal asymptote at y equals 1. There's also going to be a hole. And did we say, oh, we didn't write the hole as a point. So the x coordinate was 3, the y coordinate was 1/2. That is where my hole is. Let's plot all of those. Okay, so there's a vertical asymptote at x is equal to -3. There's a horizontal one at y equals 1. Horizontal one at y equals 1. Let me label that one, y equals 1. And this vertical one is at x equals -3. Alrighty, and okay, let's draw on the hole as well. There's a hole when x is 3 and the y value is 1/2. Okay, so the hole is at 3, 1/2. Alrighty, so looking at my sign chart, to the left of -3, my graph needs to have this shape. Okay, so that means it's going to be up here, and the reason I know it's going to be up there is because I know that as x goes to -infinity, the function is approaching 2. That was one of my limits we did. So back when we did asymptotes, under the horizontal asymptotes, when x approaches -infinity, actually I said 2, but the y values are approaching 1. And that's actually, I think, what I drew here. I think we drew it approaching the y value 1. Yeah, okay. And then in between -3 and +3, my graph needs to have this sort of shape. Okay, so in between where x is -3 and +3, this sort of shape. And I got to make sure it goes through this intercept at 0, 0. plus make it do this. And then going this way, it's going to go touch that hole. And then as I go past where x is 3, it continues that shape. It's going to continue that shape, and it's going to approach this horizontal asymptote. And I know it also approaches the horizontal asymptote in this direction because when we found the limit as x goes to positive infinity, that's going to the right. The y values, that limit was also 1. The y values are also approaching 1 in that direction. And that's what we got in the graph. As x goes to infinity, positive infinity, the y values are approaching 1. So let me just label these. So this was the hole, and 0, 0, this was the x int as well as the y int. It was both of those. And that is my graph.